Hi, and welcome to section capsule 1. For those who aren't in the loop with what section capsules are, just to reiterate, what we're going to be doing is we're going to be posting asynchronous lectures that are going to be posted on B courses. And this is going to be material that we're not going to cover during sections, but it's basically going to be quick highlights. And this is going to be, it's going to be a little bit longer this week, but hopefully in the future it'll be quick, like 20 to 30 minutes of material that we think is really important to highlight from the week section that we really want to emphasize because it's really going to be important for the material that's going to be discussed synchronously. And the actual section lectures are going to be done synchronously, but we'll upload them afterwards. So just in case you can't make them, you should be able to see them after the fact. And so in this section capsule, the first section capsule, what we're going to be discussing is we're going to be discussing the notions of utility, budget constraints, and Cobb Douglas demand functions. And so in particular, Cobb Douglas demand function is going to be super useful for the course. And so if I'm going over utility and budget constraints and you're sort of yawning and going, yes, I know all this, then I strongly encourage you to skip to the end of the video at the very least and review the general form of Cobb Douglas demand functions. It's going to be crucially important in the course, and knowing the intuition is going to really help in this week's coming section. So if the utility and budget constraints section is too slow for you, please at least watch the end of this video, as it's going to be the most important part. So hopefully this this video is going to be posted on January 24th, and this is going to be the first one. And so let's jump right in. So in the first part of class, we're going to be discussing why countries are going to be trading. We're going to be discussing other parts later, but that's going to be the major question that's going to run through the first part of the course. And so there's different possibilities that could underlie why different countries are going to trade. The first possibility is that it could be that different countries have different technologies. So certain countries are able to produce certain goods because they have different technologies than other countries, or in particular, certain countries might be able to produce certain goods more efficiently than other countries. And so that might generate trade between two countries. The other possibility is that different countries have different preferences. So for instance, if one country likes a different good than another country, they might trade so that both countries receive the goods that they favor most. And then another possibility is that they have different endowments. So they could just have different amounts of, say, natural resources, different amounts of labor, or even different amounts of sort of different endowments, such as capital or high-skilled labor, or things like that. And so in the first part, in the first section, we're only going to be looking at how different endowments are going to lead countries to trade. And so we'll come back to that in the section lecture that's going to be upcoming this Thursday. But before we start on that, first we just want to review some intermediate micro knowledge. In particular, we're going to review utility, budget constraints, and Cobb Douglas utility functions. And as I said, if you feel like the utility and budget constraints section is too slow, I recommend that at least you watch the end. So what is utility? Just to review, a utility function represents preferences of a consumer. It's going to be a function that takes values from a consumption set X, which is going to be a general consumption set. And I'll if that's sort of unclear, I'll sort of put a finer point on that later. And it's going to map them to the real line. So it's going to say, I have a bundle of apples and oranges, and it's going to map it to the number of utils that I'm going to get from that bundle of apples and oranges. And so I'm going to denote a utility function with just U. And then an indifference curve is going to be the locus of consumption bundles. So that's the different pairs of both apples and oranges, which are going to yield a given level of utility. And that's going to be U bar. And so indifference curve, if I wanted to draw it, it's going to be the different consumption bundles that yield the same level of utility. So just to put a finer point on this, let's sort of define our utility function as follows. Let's define it as being defined over apples and oranges, where apples here has an exponent of 2/3, and oranges has an exponent of 1/3. So our consumption bundles are just going to be different bundles of apples and oranges. So all we can consume here is apples and oranges. And this utility function, given the number of apples and oranges that the consumer has, is going to represent the sort of, we can call it happiness or number of utils the consumer is going to receive from consuming that bundle. And so let's just play around with inputting different numbers of apples and oranges the consumer is going to have, and let's see what utils they're going to receive. So suppose that I want this function to be equal to, oops, I was trying to draw there. Suppose that I want this function to be equal to 9. What values of apples and oranges will give me utils of 9, or so this function is equal to 9? Well, I've already done the math just to help you out, and so 1 apple and 729 oranges will give me 9 utils, or 5 apples and about 30 oranges, or 10 apples and roughly 7 oranges, or 25 apples and 1 orange. So you can see that we sort of have that as you sort of move farther out, you're consuming less of one good. You really have to have a ton of the other good to get the same utility you would get as if you had like roughly 10 apples and 7 oranges. And so you can sort of see that there's this sort of diminishing feature of utility, that as you move farther away from consuming sort of relatively equal, as you move farther away from consuming what your sort of ideal number of apples and oranges would be, you really have to consume a lot more of one good to make up for it. Similarly, if we wanted to just wanted to set this utility function equal to, I'm just going to scratch this out rather than erasing. If we wanted to have this utility function equal to 10, then we could do things like consume 1 apple and 1,000 oranges, 5 apples and 40 oranges, or I think more simply, 10 apples and 10 oranges. And so you can see as we move farther away from this sort of our ideal consumption bundle, we really have to consume, as we move away from sort of consuming equal amounts of apples and oranges, we really have to consume a lot more of oranges to make up for consuming only 1 apple. And so you can sort of see that there's a property that this utility function is sort of diminishing in marginal utility. So for a given level of u, there's u bar, there's going to be a trade-off between apples and oranges. Both weakly more apples and more oranges implies a weakly higher u. So if we just look at this row here we're consuming 5 apples no matter what, but as we can increase only the number of oranges, the utility gets higher. And so we can just see that we're holding the amount of apples here constant, but we're just increasing the number of oranges. And as long as we're holding one constant but increasing the other, we're always going to have a higher value of utility. Therefore, we're going to see that the indifference curves are never going to intersect for different values of u bar. So let's plot these indifference curves. So if I wanted to plot the indifference curve where my utility is 9, my utility is 10, and my utility is 11, I have that at the, you can recall that we had this one point where apples and oranges were 10, gave us a utility of 10. So that's that point here. On A, we can go back and see that consuming 10 apples and 13 oranges gives us a utility of 11. That's this point A here. And then we haven't mapped out 10 and 7.3, but you could imagine that it would be right there. But we've mapped out other points on the indifference curve where utility is equal to 9. So that's what these look like. And again, they'll never intersect. So we can never have one point that would give us, if these indifference curves intersected, that would mean that one consumption bundle would give us two separate values of utility. And so that couldn't be the case. Each consumption bundle has to give us a unique value of utility. And so these are never going to intersect. Okay, so now let's define the concept of marginal utility. So marginal utility is going to measure the change in total utility from changing consumption of a good by 1 unit of the said good. And so in particular, what we're going to define marginal utility to be is, suppose that I wanted to figure out marginal utility. So marginal utility of apples, for instance, or if I increase my utility function by 1 apple, how much additional utility do I get from adding that apple? And so how is this going to be defined? This is going to be defined by taking the partial derivative of this utility function. So this is the utility function with respect to apples and oranges. And I'm going to get the marginal utility of apples by taking the partial of that function with respect to the number of apples. So hopefully calculus is fresh in your mind, because that's about, we're going to take a derivative here. So we're going to take the derivative of this function with respect to apples. So in case it's a little sticky in your mind, when we're taking the derivative of this function with respect to apples, we pull down the exponent on apples. So that's 2/3. And then oranges, the stays the same, since we're not differentiating anything in oranges. And then what we get is that apples is raised to the exponent of 2/3 minus 1/3, or if I just simplify that, 2/3 minus 1/3 is negative 1/3. Okay. And so then I can notice that if I want to rewrite this, then I can get 2/3 is equal to oranges raised to the 1/3 over, and so this negative in this exponent means that we can move it to the denominator and get rid of that exponent. And so that's going to imply that we can write this as 2/3 oranges over apples, all raised to the 1/3. And so just to sort of simplify this further, each of these is raised to the 1/3, so we can just write this as 2/3 oranges over apples raised to the 1/3. Okay. And so now, just to clear my sort of messy handwriting and to sort of show you this in a little bit neater. Oh, in general, if you ever have questions about my handwriting, it's a little bit tough for me to write on this tablet. So I'll do my best to sort of write clearly, but and really, I am trying my best to write clearly on this. But if you ever have any questions, just let me know, email me. I'm happy to either sort of help you understand my handwriting, or even record a video if I look over it and it looks too bad. So I've always gotten the comment from students that my handwriting is bad. I'm sorry. I'm trying to do my best. I've even tried to sort of do a little penmanship exercises. So I promise you, I'm trying. But if you ever have any questions, feel free to email me. I'm happy to help you out. And so these are the sort of marginal utilities for apples. We can do the same for oranges, and you get 1/3 apples over oranges raised to 2/3. And so then question 3 is going to ask, is the marginal utility of apples and oranges increasing or decreasing as a function of apples and oranges respectively? Well, we can look and just see that, take apples. Well, apples is going to fall into the denominator, and that means that if we increase apples, then this function is going to go down. Likewise, if we do the same for oranges, if we increased oranges, then the marginal utility of oranges is going to go down. So both of these marginal utilities are going to be decreasing functions. That is, the more apples you consume, the smaller your marginal utility from obtaining an additional apple. And so we can see that just by going back to sort of these values that we figured out before, and we can see that 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 in order to go from having a U of 9 to U of 10, well, when we're consuming a lot of oranges, we have to consume 271 more oranges, whereas to go from whereas when we're consuming relatively more apples, we only have to consume 2.7 more oranges to go from U to 9 to U to 10. And so that's sort of hopefully helping demonstrate that these marginal utilities are decreasing. So let's move on to exercise 2. And so in exercise 2, we're going to ask, what's going to prevent consumers from having more of both apples and oranges? So the answer to that is that the consumer, like all of us, has a limited income. So eventually they have to make trade-offs between purchases of apples and oranges in order to not exceed their budget. And so what we want to do is we just want to write down their budget constraint and solve for it as a function of apples. So what's the slope of their, let's first start by writing down their budget constraint. So the first thing is, if I can only consume either apples or oranges, then I want to figure out what I'm going to spend on both apples and oranges. Well, what I'm going to spend on apples is if I take how many apples I consume, so say, let's take the unit of apples I consume, and let's multiply this by the price of apples, then that's going to tell me how much I'm going to spend on apples. Likewise, if I take the number of oranges I'm consuming times the price of oranges, that's going to be my expenditures on oranges. Okay. And so if I add up the expenditures on apples and oranges, and I can only consume both apples and oranges, then the budget constraint tells me that this expenditure must be less than whatever my income is. So that's going to be what my budget constraint is. And so what we're going to see is that their budget constraint has to be that their total income is equal to expenditures of apples plus expenditures of oranges. We can rewrite this. And so if we wanted to write the budget constraint as basically where we had oranges on the y-axis and we have apples on the x-axis, then all we need to do to write it like this is if we just take this expression and then basically all we need to do is we need to write I minus p apples times apples. That's going to equal to p oranges times oranges. So that's how you get from this first step to the second step is I'm just going to subtract p apples times apples on both sides. And then to gain this expression below, I'm just going to divide by PO over PO here. And this gives me this expression that we have here. Okay, and so if apples is the x variable here, then the slope of this is just going to be, of this line is going to be p apples over p oranges. And so that's indeed what the slides will say here. So the slope is p apples, negative p apples over p oranges. Okay, so suppose you're told that the consumer has $60 of income, the price of apples is 4, and the price of oranges is 2. Let's just write down the consumer's budget constraint. Well, they're going to buy a certain number of apples, and so we're going to take 4 times apples plus the price of oranges, and so that's 2 times the amount of oranges. And we know that this must be less than or equal to the consumer's income. And so that's going to be the consumer's budget constraint. And so written out a bit more clearly, that's what the slides have to say. So let's draw the consumer's budget constraint. At which point is the consumer's utility fully maximized given their budget constraint? So we're going to go back to that graph that we drew before, but let's just figure out whenever you want to draw a budget constraint, you just want to figure out what's the maximum amount of both apples and oranges they can consume, and that's going to tell you what the x and y intercepts are going to be of the budget constraint. So suppose that we consume 0 oranges, and so this was nothing. Well, then if we consume 0 oranges, and recall that we said that oranges were going to be the x-axis. So if oranges were going to be 0, then this means that we could consume 60 equal to 4 times apples, and so 60 divided by 4 is equal to 15. And so that tells us that we could consume 15 apples, and that would be the y. So if we want to take this on the graph, oh, I'm sorry. This needs to be reversed. So, sorry. Oranges was earlier what we had for the y-axis, and apples was what we had for the x-axis. So excuse me. So oranges was y. If oranges is 0, then we can consume 15 apples. And so if we want to mark this point here, we're consuming 0 oranges. Remember, the oranges is the x-axis. Sorry, excuse me. I keep making the same mistake. Oranges is the y-axis, and so that's 0. And then apples is the x-axis, so that's this point here. And likewise, let's just now suppose that we consume 0 apples. So apples is going to be the x-axis. Excuse me. And so that's going to mean that oranges, which is going to be the y-axis, is going to be given by 60 divided by 2, so that's going to be 30. So that's going to give us this point right here. And so if we draw a line in between these 2 points, we get our budget constraint, which is drawn as shown. Okay, and so just to come back to the last part of the question, 3, at which point is the consumer's utility maximized given their budget constraint? Well, we can see that it's going to be this point B, and this point B is going to be precisely where their budget constraint just their budget constraint just kisses this utility function, and so it's going to be at this point B. And so let's just work through which point is going to give us the maximum possible utility. Well, point A we can see is going to give us a higher utility. It's going to give us a utility of 10. But our budget constraint is to the bottom left of point A, and so our consumer would love to consume 10 apples and 13 oranges, but they can't because they can't afford it. Similarly, if we think of point C and D, we can attain it. You can see that points C and D both intersect with our budget constraint, but they don't give us as high of a utility. So if the consumer would rather change, would sell or trade or barter the number of oranges they had here to gain a little bit more apples, they would be better off if they just only had 10 apples and 10 oranges, and so they'd never consume C or D because they'd be better off just consuming at point B. And so the optimal point here is going to be point B, and that's going to be where the indifference curve, this indifference curve is going to be just tangent to the slope of our budget line, as seen on this graph. So what did we find? We found that the optimal utility maximizing bundle is going to occur at the point where the slope of the budget constraint is going to be equal to the slope of a tangent line to the indifference curve. And so algebraically, what we're going to express this as is that the slope of the indifference curve at a given point needs to be equal to the slope of the budget constraint. And I have this in absolute values. So remember that we said that that the slope of the budget constraint in this example was going to be P apples over P oranges, negative P apples over P oranges, but we're going to ignore that negative. And so we're going to have that. And so, okay. So as I said, the slope of the budget constraint is P apples over P oranges. What's the slope of the tangent line to the indifference curve? Well, this is called the marginal rate of substitution. And what it formalizes is it formalizes the amount of oranges one must give up to obtain another apple while maintaining the total utility constant. And so this is going to be defined as the marginal rate of substitution is equal to the marginal utility of apples over the marginal utility of oranges. And if you recall, the marginal utility of apples is equal to the partial derivative of the utility function with respect to apples over the partial derivative of the utility function with respect to oranges. So putting all of that together, excuse me, what we get is we get that our utility maximizing consumption rule is going to be to have the marginal utility of apples over oranges equal to the ratio of prices. And so that's going to be our utility maximizing consumption rule. Okay, so what we're going to do is we're going to, now what I'm going to do is I'm going to present, hopefully that sort of, you've seen all of that before. And, you know, I didn't go through all of that in full detail, but hopefully you saw it all from intermediate micro, or at least hopefully a lot of the details are coming back to you now. So above, when we defined our utility function, this utility function here, over apples and oranges, what this utility function is technically of the form, oh, sorry, I'm drawing way too big of a circle, but you see that I'm referring to this utility function right here. Sorry, it's hard to write on these tablets. This is of the form, which is called Cobb Douglas utility. And so this is going to be by far and away the most common type of utility that we're going to see in this course. And with Cobb Douglas utility, it's important to note that the optimal consumption bundle is always going to take a particular form, which means that as I go through the full steps to show the general solution, you're not going to, you know, I'll show it to you just for your reference, but you don't always need to derive the full steps above to solve for optimal consumption bundles. And so I'll show you how to derive the general solution, but in general, then I'm going to show you basically an intuitive rule for the general solution. And if you take it and memorize that, then you'll be well prepared for the course, because we're going to see a lot of Cobb Douglas utility functions. So please stick around and wait for the last part of the video where I talk about the intuition behind these utility functions, because it's really important. So let's jump into the general solution. So what we're going to do is similar to above. We're going to assume that the consumer has a utility function that's defined over two goods, not oranges and apples now. It's just going to be x and y, with two exponents, alpha and beta. Then the marginal rate of substitution, again, is just defined as the ratio of marginal utility over x over marginal utility over y. And so recall that marginal utility over x is just defined by the partial derivative of u with respect to x. And so that's going to be equal to, so if we take the derivative of this function with respect to alpha, you just pull the alpha down, subtract 1, and leave y beta alone. And then if you take the derivative of this with respect to y, as we do below, then you just pull down beta, and then leave x to the alpha as it is, and then subtract 1 from the exponent. You get this. And then if you note, if you just subtract these exponents off, so if I'm subtracting this exponent, that gets us b, negative b, plus 1. So these cancel out. And so we're left with y raised to the 1. And then likewise, we can do the same here. These alphas are going to cancel out. So we're left with x to the 1 on the bottom. And so our MRS here is going to be alpha over beta times y over x. And so now what we want to bring in is we just want to bring in the rule that we had before, that the MRS should be equal to the ratio of prices. And so if we're going to let the price of the good x be px and the price of good y be py, and the consumer's income bi, then you can sort of quickly see how we're going to get back to the optimal consumption rule. So again, I'm just restating that the consumer's budget constraint is going to be the expenditures on x, where I'm just abbreviating that as expend on x. This is going to be expenditures on y. And again, that, you know, if they're maximizing the utility, they're going to consume, they can only consume x and y, and so they're going to eat their consumption, if they're maximizing their expenditure, is just going to be equal to their income. And so coming back, you know, we saw the utility maximization rule that's going to give us that the MRS has to be equal to the ratio of prices. And that's going to be, again, recalling what we saw earlier, the absolute value of the slope of the budget constraint. Okay, so this rule is going to tell us how we need to consume X and Y optimally given our budget to maximize our utility. Okay, and so we're not going to be able to consume infinite amounts of X and Y. We're going to figure out how we can maximize our utility function U subject to not spending any more than our budget. Okay, so we can do a couple things. The first thing is we want to solve for Y in terms of a function of X. So if we start with alpha over beta Y over X equal to PX, first thing we want to do is we just want to write Y as a function of X, and then we can then what we can do is we can plug in for either Y or X and then solve from there. So let's just write Y as a function of itself to start with. So the first thing what we want to do is we want to multiply by beta over alpha on both sides. And so that does a little bit of simplification, and then we can multiply by X on both sides to get us, as we've written here, Y is equal to alpha over beta PX times X. Okay, and so then what we can do is suppose that we want to just solve for Y. Then now that we have Y as a function of X, we can just plug, if we take our budget constraint, which, recalling that our budget constraint is expenditures on X plus expenditures on Y equal to our income, then what we can do is we can plug in this Y in here. And now if we just see Y is only a function of X, then as soon as we plug this in here, we have an equation in which Y no longer shows up. And so we can write X as only a function of the prices of X, Y, alpha and beta, and our income. So let's do that. So again, this expression, in this expression, we've just plugged in for Y here. And so now let's just make a couple of simplifications. The first simplification that we can make is we can see that these PYs, or the price of Y, is going to cancel out here. So that's the first thing that we can do. The second thing that we can do is we can notice that there's these terms PX, X in both the first part and the second part on the left-hand side. So what we can do is I'm just going to pull out PX times X, and then what I'll be left with is I'll be left with 1 plus B over alpha, and that's going to be equal to I. So the last thing that what I'm trying to do is I want to just solve for X by itself. So that was the whole reason that we were doing this from the first place. So let's make a couple of simplifications. So the first thing is, and this is going to be important because I'm gonna try to get this term on the other side, is I'm just going to try to combine this one term and this B over alpha term. So to get rid of this one term, I'm just going to multiply 1 by alpha over alpha. Notice that alpha over alpha is just 1, so these are the same. And add this to beta over alpha and equal to I. So what does this simplification give me? It gives me PX times X, that hasn't changed, is equal to alpha plus beta over alpha, and that's equal to I. Okay, so now we're seeing how I'm going to do this. So all I'm going to do now is I'm just going to multiply on both sides by alpha over alpha plus beta. So I'm going to multiply by alpha over alpha plus beta. These both cancel out. And so what I'm left with is X equal to I. And again, I'm just going to divide by PX here. So what I'll be left with is I'll be left with X, the optimal X is going to be equal to I times PX times alpha over alpha plus beta. So that is our optimal X. Now, how do we find our optimal Y? Well, that's pretty easy. All we're going to do is we're going to come back to this function here, and we're going to plug in for x. So let's take down this function right here. So I'm just going to carry this down. Oops. Oops. So I'm going to carry this function down here because, again, we just want to figure out what, now that we figured out our optimal x, let's figure out our optimal y. And so all I'm going to do here is I'm going to take this x here and plug this in up here. So what is this going to give me? Well, it's going to give me alpha beta over alpha times px times py times I over px times alpha over alpha plus beta. So these px's are going to cancel. These alphas are going to cancel. And so what I'll be left with is I'll be left with beta over alpha plus beta times I over py. Okay, and so just to conclude and maybe write a little bit neater, y star, or sort of the optimal amount of y that the consumer is going to consume given their budget constraint, is going to be equal to y star. Okay. And so just to show you that, but a little bit cleaner, we have the optimal x and y star given by what I just did. So one simplification we can make is whenever alpha plus beta is equal to 1, and this is going to be the case for pretty much the entire course, then the general solution is simplified because this is just 1, this is just 1. And so then we have x star is equal to alpha times I over px, or the price of x, and y star is equal to beta times I over py. So this is important because now written like this, the general solutions actually have a very interpretable form. So note that if I just multiply this first term by px on both sides, then these cancel out. And what I get is I get that px times x is equal to alpha times I. And again, if I just multiply by py on both sides of this expression, then I get that py times y is equal to beta times I. But note that alpha and beta sum to 1. And so when alpha and beta sum to 1, they represent the shares of income that the consumer's expenditures on px and py compose. So remember how I said that px times x, well, that's going to be my expenditures on x. Because, you know, if I just take the number of goods x that I'm consuming times their price, then that's telling me how much I'm spending on x. And so if alpha is my income, then, if I is my income, then alpha is going to tell me what the share of income I'm going to spend on, I'm going to spend on x. And likewise, if I take py times y, then again, this term is going to be expenditures called exp on y, and then, oh, sorry, this should be a multiplied by, excuse me, sorry. Then expenditures on y is just going to be equal to beta times I, where again, oh, shoot, yikes, sorry about that. Where again, I is equal to income, and then beta is the share. I'm sorry, I'm having a lot of technical issues. Share of income spent on y. Okay, and so whenever someone gives you a Cobb Douglas utility function, and this is what exercise 3 is going to be, then you don't actually have to do any math to figure out what the optimal consumption of say 2 goods is going to be. And the reason is that you can just use your general intuition to apply it to any given utility function. So recall our example from earlier where the utility function defined over apples and oranges was equal to apples 2/3 and oranges 1/3. And assume that prices and income are the same. Just to reiterate, we said that income was 60. I think the price of apples was 4 and the price of oranges was 2, but that might be reversed. Let me double check. Yes. And so now what we want to do is we want to solve for the consumer's optimal consumption bundle just using the general form for Cobb Douglas utility. So what we know is that this exponent says that we're going to spend, our consumer is going to spend 2/3 of their income on apples. So what does it mean to spend 2/3 of your incomes on apples? Well, it means you're going to spend 2/3 times I, that's your income, on expenditures of apples. And recall, expenditures of apples is just the price of apples times the amount of apples you consume. So if we just divide by PA on both sides, that's going to give us the rule that the optimal consumption of apples is just equal to 2/3 times I over PA. And note that those cancel out, so I can just get rid of those right there. Okay, but note that if I know that the price of apples, again, from before was 4, then I can just plug in for 4. And I know that my income is 60. So I can just plug in for these numbers. And now you can see that these numbers are nice and pretty. And so I can just cancel out a lot of things. So this 2 cancels out with this 4 to become 1/2. And the 3 is going to cancel out with 60 to become 20. So this is going to be now 20 over 2, or just simply 10. Okay. Likewise, I can do the same thing for oranges. So oranges, this having an exponent of 1/3 means our consumer is going to spend 1/3 of their income on oranges. And so what we're going to have is we're going to have that price of oranges times oranges is going to be equal to 1/3 times income. So if I just divide by the price of oranges on both sides, then these cancel out and I can just get rid of that. And so my consumer's optimal amount of oranges will be given by 1/3 times income over the price of oranges. Again, we know that income is 60 and the price of oranges is 2 from before. And so what is that going to leave us? Well, the 3 again is just going to cancel out with 60 to make 2. And then this is going to be equal to 2 over 20 as before. And so my consumer's optimal consumption of apples and oranges is simply 10 of each. And this is just showing that hopefully a little bit more clearly. So now all we needed to know is our consumer's utility function, the prices and their income, and we were able to figure out what the optimal consumption was of apples and oranges without having to do things like equating marginal utility of apples over oranges to the price of apples and oranges. So that's a lot more work. And so instead, we can just use the heuristic that the exponents in the Cobb Douglas utility function represent expenditure shares, and then figuring out a consumer's optimal consumption bundle becomes very easy. And so hopefully this made sense, because this is going to be pretty crucial in the class. If you have any questions, please email me, but hopefully this will help section this upcoming Thursday make some sense. So looking forward to seeing and meeting everyone then. Thanks so much and take care.